So we're going to have to take a little trip into physics here. One of the ways that atoms behave, electrons behave, are as waves. And so we need to talk about light and how light behaves to help us understand this. So what is light? You ever thought about that? I mean, we know what it does. You turn the lights on and then we can see what's going on, right? Got up this morning and it was really dark outside. There wasn't any light. What is light? Light is a form of electromagnetic radiation. So electromagnetic, it has an electric field and it has a magnetic field, and these fields are traveling through space. And that's what light is. It's a form of energy. So it's got perpendicular, meaning at right angles to each other, oscillating waves, meaning they're going up and down. They're increasing and decreasing. An electric field is a region in which if you have an electrically charged particle, it will experience a force. It'll be attracted or repelled by the electric field. A magnetic field is where a magnetized particle experiences a force. All electromagnetic waves move through space at the same speed. It's a constant speed, it's always the same, and because it's the speed that light travels at, we call it the speed of light. Okay, so the speed of light is 3 times 10 to the 8th meters per second, which is really, really, really fast, right? So here's an illustration of these oscillating waves. So in red, we're looking at the electrical component, and so this field increases and decreases. It's the form of a sine wave as it travels through space. The magnetic component is oscillating in a perpendicular plane. And both of these fields are traveling together at the speed of light. Any questions? So this is a picture of lightning. And I think we all understand that you see the lightning and then you hear the thunder later. The thunder is the sound of the lightning, but there's a delay in what we see and what we hear. And you sometimes even can observe this in a large stadium, where you see the person talking, but the sound doesn't come until a little bit later. And so you get this delay, and it's kind of disturbing. It's hard to listen to. So why does this happen? Well, we see the lightning, and that light travels at the speed of light, 3 times 10 to the 8th meters per second. But sound travels at a much slower rate. Sound travels at 340 meters per second. So if you're sitting over here, you see the lightning, it takes longer for the thunder, the sound, to get to you. And this is how you can use the delay between the two to predict how far away that lightning strike was. Because the farther away it is, the longer the gap between. Any questions?
Actually, I got one.
Uh-huh.
So if you got struck by lightning, would you hear it as well?
If you got struck by lightning, yeah, you'd hear it. And it would be simultaneous. Has anybody ever been near a lightning strike? Yeah. There wasn't much delay, was there? And it's really loud. I've never, been struck by lightning. Not many people have and live to tell about it. But I've been near, like when a house just a couple houses down got struck by lightning. It was really, really loud.
The dog went nuts.
Oh yeah, dogs don't like that. Small children don't like that either. So light is oscillating fields, and these behave as waves. So we need to understand, how can a wave be described? Well, we can quantify different aspects of waves. Amplitude is one of them. This is how tall the wave is. And the waves, these oscillating fields, we can't see the oscillating field, but it does behave much like waves on water. And so we've observed waves on water, and so the waves of electromagnetic radiation behave in much the same way. So the amplitude is how tall the wave is. So if you think about going to the ocean and big waves come crashing in, and sometimes the waves are really, really tall, and other times they're much shorter. That's the amplitude of the wave. So we call this the crest of the wave. This would be the trough down here, the bottom. I can't get down there. There, down there. And this is the node. This is where it crosses. You know, if you think about this, you could call this the zero line, and this is positive and negative, and it goes back and forth across this line as it travels. So the distance from this 0 point to either the crest or the trough is going to be symmetrical. Amplitude corresponds to light intensity. So if the light is very bright, that's a large amplitude. It's an intense light. If the light is dim, it's a low amplitude. We can also measure the wavelength, and this is given a Greek letter as its symbol, as the symbol lambda. And you know, if you haven't seen that one before, it's kind of weird. It's a bit like an upside down lowercase y. Okay, so lambda. This measures the distance from the crest of one wave to the crest of the next wave. So from this peak to this peak, or you could measure from the trough to the trough. It's how long the wave is. And so this would be the distance between those waves coming in on the ocean. Any questions? So here we have different amplitudes. So this is a lower amplitude. This is a higher amplitude. And so for light, that corresponds to dim light or bright light. If the wavelength changes, we perceive that as different colors of light. So red light is going to have a longer wavelength, yellow's in the middle, and blue is going to have a shorter wavelength. Okay? So you could have a bright blue light or a dim blue light. It's going to have the same wavelength. You could have all bright light and change the wavelength, you change the color. Another thing we can talk about in terms of waves is frequency. Frequency is given the Greek letter nu, which is like a V that's a little bit curved. And that can be a little confusing because it looks an awful lot like an actual V, which is for velocity. The frequency is the number of waves that pass a point in a given period of time. So if you're standing in the surf at Pismo and if you count how many waves crash into you in 5 minutes, that would be the frequency of those waves. You know, this many waves per 5 minutes. Usually we measure it per second. So we count the number of waves or the number of cycles per second. And that tells us how frequently does this event occur. And so cycles per second is called a hertz, not the rental car company, but hertz, and it's abbreviated capital HZ. That's cycles per second or waves per second. So 1 hertz is 1 per second. And we understand that to mean one thing, one occurrence per second. So the total energy of a wave is proportional to the amplitude, how tall it is, and the frequency, how frequently it occurs. So if you think about standing in the surf, those waves have energy, don't they? As they crash into you, you feel the force of them. They have energy. Which has more energy, a really big wave or a small wave? A big wave, right? Really big wave might knock you over. If you've got small children with you, it probably will knock them over. It has more energy. Little tiny waves are not going to knock you over. So larger amplitude is more energy. The frequency, if you're standing there and you get one wave every 10 minutes, you're not really going to notice. But if there were waves coming every 30 seconds, you're going to feel pounded, right? All this energy banging into you. Yes?
This is what happens to surfers when they fall in the break zone. They just get pounded.
Right, because as the waves come in, they change, which is different than electromagnetic radiation. But at some point, those waves are breaking, and yeah, you don't want to hang out there because they're just constantly coming on top of you. So larger amplitude, more energy, more force, more frequently that wave is hitting you, the more total force there is. You guys okay with that? So there's a relationship between wavelength and frequency. Because how fast are these waves traveling, electromagnetic radiation? Speed of light. So all these waves are traveling at the same speed. Okay? They're all traveling at the same speed. So if they're all going at the same speed, then their frequency and their wavelength are going to be related. So I'm going to draw an ugly picture here. I didn't mean for it to be that ugly. So here's a person. So two waves. Let's call them A and B. Which wave has a longer wavelength? A. A has a longer wavelength. So if I'm standing here and these waves are coming at me at the same speed, which wave is going to hit me more frequently? B, because it has a short wavelength. So short wavelength corresponds to high frequency. Long wavelength corresponds to low frequency, because this is not going to hit me as often, as frequently. Okay? So the relationship here, the frequency is equal to the speed of light divided by the wavelength. So the larger the wavelength, the smaller the frequency. Any questions? C is the abbreviation for the speed of light. Color. The color of light is determined by its wavelength. The wavelength is related to the frequency, so we could also say it's determined by its frequency. So what we refer to as white light is actually a mixture of all the colors of visible light. And this is the sort of light that comes from the sun or from an incandescent light bulb. There's a spectrum of different wavelengths. And you should learn the order of these colors. So if you separate them, and you can separate them with a prism, because as the light goes through these surfaces, the air and the prism material have different indexes of refraction. And so they're going to bend the light at different angles depending on the wavelength of the light. So it goes through this junction, and through this junction it's gotten bent twice, and that causes the wavelengths to separate out, and you see a rainbow. And so when we actually see a rainbow in the sky, it's little droplets of water acting as prisms, taking the white light from the sun and separating it into the different colors. They will be separated in the same way every time. So we see the rainbow here, and we see that red is on top and violet is on the bottom. And the order of the colors is all the same because the order of the wavelengths of those colors is the same. So it's red, orange, yellow, green, blue, indigo, violet. And the way I learned to remember that was Roy G. Biv. Roy, having trouble here. G, Biv. So kind of like somebody's weird name, like his first name's Roy and his middle initials G and his last name's Biv, right? Red, orange, yellow, green, blue, indigo, violet. This is why sometimes when children draw rainbows, it's like, beautiful job, honey, but you're thinking, something's weird looking about this rainbow. Because we recognize as adults that the color order matters. Children don't recognize that. And so they'll sometimes just draw the colors in random order. And we recognize they're trying to draw a rainbow, but it's not quite right. So why do things have color? Here we have a picture of a woman looking at a laptop, and she has a red shirt and blue jeans. Why is her shirt red? What makes something red? Well, you put red dye in it, right? Well, why does the dye make it appear red? Why do things appear different colors? It's because of the light that's absorbed and reflected by the components of the shirt. So a red shirt will reflect the red light. It will not absorb the red light, and it will absorb most of the other colors. So what our eye sees, the white light hits the shirt, most of the colors are absorbed except the red, and the red bounces off, and we see the red. What happens with a black shirt? It absorbs all the light. This is why, like a black lab or a black cat, black animals are very hard to photograph because they just absorb light, and so it's really hard to get any contrast on them, and they often end up looking like blobs, right? So black absorbs, white is reflecting all the light. And we know this from experience. If you go out in the summer and you're hanging out in the sun, which is going to be hotter, a black t-shirt or a white t-shirt? Black t-shirt. Because the black is absorbing the light. A white t-shirt is reflecting the light. Light is a form of energy. A black object will get hotter faster than a white object. Any questions? So the color we see for an object is the color that's being reflected. Yeah?
What about colorblind people?
What about colorblind people? That's an excellent question. So I have 5 sons, and 4 of them have some degree of color deficiency. So this gets more into biology, but I think it's applicable here. So vision, we have different sorts of rods and cones, and one senses just light in general, and the other distinguishes between colors. And so really what we're seeing are 3 colors, and our brain interprets that as color. So someone who's color deficient or color blind, that does not mean that they see the world in black and white. It just means that depending on the deficiency, they may only have one set of, I think it's cones, isn't it? Anybody know?
Yeah.
That do the color, yeah. They may only have one set of cones, or 2 instead of 3. And so that affects how they perceive light. And so really what color blindness is, like my kids have a red-green deficiency. And that doesn't mean that they can't see red or they can't see green. If you give them a red crayon and a green crayon, they can identify which is which. But if you get into muddy colors in between, they look the same. And sometimes even those bright colors, really weird experience my oldest had when he was in elementary school. They played a game where they threw paper clips, brightly colored paper clips, into green grass. And it was a race to see, this team had to pick up this color, another team had to pick up that color. He couldn't see the red ones. He could not see the red paper clips in the green grass because it looked like the same color to him. And so it's a very, very odd thing. And you can go online, and there are different programs and stuff that can help to simulate what a colorblind person would see. It's pretty interesting. I had an uncle, and he said, who's very colorblind, he says in the spring, the grass is the same color as the fire trucks. Looks the same color to him. Later on in the summer, the grass color Changes a little bit. Later on in the summer, they're different colors. But in the spring, when the grass first comes out, same color as the fire truck. Now, does that look like red to him? I don't know, but those two colors look the same. Any other questions? Okay, a math example here. A laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency of the light. So there's an equation for this. Frequency, oh, good grief, having stylus issues today. Frequency is equal to the speed of light divided by the wavelength. I don't expect you to memorize the speed of light. I would give that to you on an exam. The speed of light is 3.00 times 10 to the 8th meters per second. Divided by the wavelength, here the wavelength is 515 nanometers. Always write the units and look at them. What is a unit for frequency?
Hertz.
Hertz, which is per second, or second to the minus 1. So here we have second in the denominator of this fraction, so that's a good sign. But do we want meters and nanometers in there? No, we want those to cancel out. Do meters cancel with nanometers? Not so much. So we could take nanometers here separately and convert it. Or a short way to do this is to say, well, 515 nanometers. Nano means 10 to the minus 9. So instead of writing the n, I'm going to write what it means. So I'm going to erase this. And nano means 10 to the minus 9, and there's meters. So 515 nanometers is the same as 515 times 10 to the 9th meters. That's not proper scientific notation. It's okay. Your calculator will understand it. So now we have meters, and those are going to cancel out. So I've got 3 times 10 to the 8th divided by 515 times 10 to the minus 9. And this would have 3 significant figures. 5.8252 times 10 to the 14. And the unit is 1 over second. Or you can write that as s to the minus 1, or you can write that as hertz. And rounding that to the correct number of significant figures, 5.83 times 10 to the 14th per second. Any question? That's a big number, isn't it? But this is light, which is traveling extremely fast, and the wavelength is really, really small. So in 1 second, 5.83 times 10 to the 14th of those waves are going to pass a point. So we talked about rainbows, and that's a spectrum, a range of different wavelengths. We can also look at the overall electromagnetic spectrum. Visible light is only one teeny tiny part of the entire electromagnetic spectrum. Radiation with shorter wavelengths is higher frequency. That's higher energy. Things with longer wavelengths are low frequency and have lower energy. So at one end, we have radio waves. Radio waves are the same phenomenon as visible light, but they are just a much longer wavelength than visible light. These have very low energy. And gamma rays have very high energy, very short wavelengths, high frequencies. High energy electromagnetic radiation can damage biological molecules. So you go outside, you spend all day out in the sun, and what might happen? Sunburn. You can get a sunburn. Some of us burn much easier than others. You get a sunburn. How does that happen?
Too much sun.
Too much sun. What about the sun is damaging your skin? It's the light, right? Specifically, it's the ultraviolet light, which is just a little higher in energy than visible light. It's higher in energy, and over the course of 15 minutes to hours, depending, it can damage your skin. Too much energy gives you a burn, right? If you stick your hand in boiling water, there's too much energy, it's going to damage your skin, right? One of the ways that higher energy radiation damages biological molecules is by taking those molecules and making them into ions, by knocking electrons off. And when you make something into an ion, then it behaves differently and it messes up all the biochemical reactions that are occurring. Okay, so here is the whole electromagnetic spectrum. So I know it's really big and colorful, but try to ignore this part for now. So here we have their names. Down here, low energy, radio waves, microwaves, infrared, visible light is this little tiny portion here, ultraviolet, X-ray, and gamma ray. We have two scales here, frequency and wavelength. So the wavelength for radio waves is very long, 10 to the third meters. That's a kilometer. So on the scale of a mile, a wave that has a mile wavelength, that's really long. And at the other end of the scale, 10 to the minus 15th meters, really, really tiny. So this wavelength is getting shorter and shorter and shorter. That's higher energy. Up here we've got the frequency. The frequency is inversely related, and so we have low frequency here and high frequency there. This part is the visible light. And because that's a part of the spectrum that we're very interested in, we're zooming in on that, and so this is the zoomed in portion. So here the wavelength is given in nanometers because that's the unit we typically use. It gives us reasonable numbers. So ranging from 750 nanometers, the longest wavelength, to 400 nanometers, the shortest wavelength of visible light. Ultraviolet light is just higher in energy than visible light, and that's why it can cause damage. So in your textbook, there are sections about microwaves, infrared, etc. You should read those. Okay, I'm not going to read them to you. Sometimes when students look at this table, especially when they're answering the questions for experiment 7A that we're doing on Wednesday, they misinterpret the table. And you may be asked, which has higher energy, microwaves or red visible light? And they'll say, well, here's a microwave and here's red light, so the microwave is higher in energy. No, this is zoomed in. The red light belongs here relative to the others. We just pulled this apart so we can see it. But red light is in here. Microwaves are actually lower in energy than visible light. Infrared is below red, and ultraviolet is above violet, if that helps you remember. Any questions? When we separate white light using a prism, we get a nice rainbow. This is a continuous spectrum. We see just the gradual transition from one color to another There aren't any gaps or anything. This is a continuous spectrum. It's showing us all of the wavelengths. Thermal imaging uses infrared light. So this is a picture I took at the Jet Propulsion Laboratory down in Pasadena, NASA's lab down there. They have this camera. So we're standing in front of the camera, and the visible light gives you a picture like this, and the infrared camera gives you this image. So we are all giving off infrared energy, electromagnetic radiation. That's the energy that is coming from warm objects. So it's basically a form of heat. So we see here the warmer parts are red and the blue parts are cold. That didn't make any sense, did it? The warm parts are red, the cold parts are blue. There we go, that's better. So night vision, you may have seen some pretty cool videos available showing night vision. Seeing in the dark. Well, what are you actually looking at? You're looking at a camera that detects infrared radiation. And so it detects warm objects versus cold objects. And so you can find a person hiding in the woods in the dark using an infrared camera because they are warmer than their surroundings. And so you can see them. Do you actually see them visibly? No. You need the camera and the interpretation from the electronics to give you a picture. Any questions? We use electromagnetic radiation for all kinds of things. And I think the word radiation is kind of scary, isn't it? In society, radiation is a bad thing. Well, all of the entire spectrum of electromagnetic radiation is radiation. It's just something that radiates. It's a form of energy. Some of it's dangerous, some of it isn't. But we can even use the dangerous stuff to give us positive outcomes. High energy radiation like gamma rays are very destructive to living tissue. But we can take advantage of that to kill cancerous tumors. So say you have a tumor inside your brain where they can't go in and cut it out because in the process of cutting it out, they're going to damage the rest of your brain, the healthy tissue that you need, and so they can't go in and surgically remove it. But you can use radiation to go in there and kill it. Now, of course, you can't just zap it through in one place because then again, you're damaging the healthy tissue, and that might be almost as bad as cutting your hand open. So what they do is they direct the radiation from different directions, and they do multiple beams that aren't too strong. So it does cause a little bit of damage to the healthy tissue, but it causes damage to the tumor also. And because the tumor is the focus of all of these beams, the tumor gets a really big dose. So this is a way that you can kill tumors without damaging the brain so much that it's not helpful. Another thing that waves, a characteristic of waves is that they can interfere with each other. So when two waves interact, it's called interference. And this interference can be either constructive or destructive. So here we have two waves that are in phase. And what this means is that the peak of one lines up with the peak of another. And so as they're going through space, they're both at a peak and a trough at the same time. They're going together. If those interact, they will essentially add together, and their amplitudes will increase. That's called constructive interference because it makes it bigger. If you have waves that are out of phase, where the peak of one lines up with the trough of another, it's destructive interference, and it essentially cancels out if they're exactly out of phase in the same amplitude, and you get nothing. So destructive interference is utilized in noise-canceling headphones. So how can headphones cancel the noise around you? Well, what they do is they take the noise, that background noise that's distracting, and they shift it, they shift the phase and play it back through the speakers, and so those two waves then cancel each other out, and you don't hear anything. Any questions? So waves can interfere. We also observe diffraction. And what this means is if you have a traveling wave and it encounters an obstacle or an opening in a barrier that's similar in size to the wavelength, the waves will bend around that obstacle or through that opening. So this is different behavior than particles. Traveling particles do not diffract, but traveling waves do. If you have two openings that are close together and you have waves diffracting through both of them, the waves that are diffracted can interfere with each other constructively and or destructively and cause a pattern called an interference pattern. This is a characteristic of all light waves. So all forms of electromagnetic radiation can do this. So that might look like this. So here's a wave, and what we're seeing here is just the tops of the waves. So as the wave comes through, here's the wave crest, and it goes through, hits this barrier, and there's a little opening. So part of these waves can go through, and as they go through, they get bent. And so then we would see this curved wave after that, a bit like a ripple, right? You drop a drop of water into still water or a stone or something, and it causes ripples that go out in concentric circles, right? If you have particles, and particles coming at that same barrier with the hole in it, they are either going to hit the wall or they're going to hit the opening. And if they hit the opening, they just go straight through. If they hit the wall, they stop. They don't, or they bounce back. But particles do not diffract like waves do. So this is an illustration of what's sometimes called the double slit experiment. So here we have a light source, and the light here is coming out, it's radiating, so it's going out in all directions. Since it's coming from the same source, it's all going to have the same, is going to be in phase, right? It's a regular pattern coming out here. So here we have two slits, and those slits are similar in size to the wavelength of the light. As the light hits this slit and goes through, it diffracts and becomes curved. And light hitting this other slit will also curve. Now we have the light coming out here, and instead of traveling in one big concentric circle, it's in two. And as these two overlap with each other, we're going to get places where there's destructive interference, where the waves are out of phase, and that will give us a dark spot on our detector. And waves that are in phase will be extra bright and will give us a bright spot. So as the light travels through here and undergoes constructive and destructive interference, what we observe on the film here is a series of light and dark bands. And you can do calculations. The distance here, you can get what the wavelength is and all kinds of fun stuff that we're not going to do any of that. Any questions? So here's another video that this is one of my favorite videos.
What is light?
What is light? Light from below. What is light? That's a good question. What is light?
Isn't it an element?
Light is brightness, I guess.
We have auras,
We all have auras.
which are light.
Yes, they are. It lights up the room. It makes it not dark.
What's the difference between blue light and red light?
It goes in your eyes and then you see stuff.
They range from white to red, to orange, to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, right,
Yeah.
it would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles, or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment I've recreated today. Thomas Young's double-slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803.
I brought into the sunbeam a slip of card, about 1/30th of an inch in breadth, and observed its shadow, either on the wall or on other cards held at different distances. Besides the fringes of colors on each side of the shadow itself was divided by similar parallel fringes of smaller dimensions. Wow.
This is an experiment so simple that you could make it at home, and yet so fiddly that I've never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box, taking it out on the street.
Could I possibly interview you guys for about a minute? We're doing a science experiment.
I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm going to place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom?
Well, the obvious thing you think you're going to see is you're going to see two lines.
Two lines on the bottom of the box.
Two bright bands.
Two little
And
ones.
then
Yeah, I think it'll be one line instead of two.
I can expect to see the whole box lit up.
That can be a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, different colours.
There, have a look. You expected to see kind of one line. Is that what you see?
I
No.
see dots.
How many?
It's one circle.
Well, there's one in the middle strongest, two either side.
The two on the outside are multicolored. The one in the middle is just white.
Like kind of a rainbow?
The rainbow of colour as well. Quite a few colours and lots of little dots.
But there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
Two slits.
two slits. That's incredible.
But all we're doing is we're putting a light through two very narrow slits, side by side. How does this make any sense?
There's some kind of principle involved there. The average person's not familiar with. That's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern.
You see that?
This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up, peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there. It's light cancelling itself out.
This is basically the same as like having 2 drops of water fall in a swimming pool.
That's right.
Exactly the same
And they go and
pattern.
overlap. As this ripple overlaps with those ripples, down the bottom, you get a series of, you get like a bright spot, and then a dark spot, then a bright spot, then a dark spot, then a bright spot.
Now there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what caused the rainbowing effects as we go further from the central maximum. So you saw the ones to the right were slightly colored.
Yeah,
that's
that's
because
working.
the reds are going to meet up at different places than the blues.
And that's all that makes the colour differences, is different wavelengths.
Exactly.
That's amazing.
So the difference
So
between
there's
red
still
and blue,
that red bin over there, the green part, I'm seeing
It's a
that, it's
different-
just different
different
wavelength. And that's how we bring in all these beautiful colours all around us.
exactly.
That's amazing. I'm amazed. Oh, good on you, thanks, Ben.
Hey, thank you.
I have been enlightened. Literally.
Sometimes the simplest questions have the most amazing answers. Like,
Is there a speed limit in the universe? Where does the sun get that energy from? Where do they get the matter to make the tree?
So that's another channel full of interesting videos. But now that we've seen that, let's look at this diagram again. One of the things, besides that, the guy with the baseball cap who's just like blown away, that's always fun to watch. One of the things I like about this video is they do the ripples on the water. Because we can see water waves. And so the ripples are really cool. So he had 2 sources, and the 2 sources would represent the waves coming from one slit and the wave coming from another slit. And as those waves travel out, they interact, they interfere constructively and destructively, and that's how we saw those sort of lines radiating out, where some of it was a higher wave and some of it was basically no wave at all. Does anybody have any questions? Does that make sense? Okay, so that's wave nature. Turns out that light, which we understand to be a wave, can also behave as a particle. And so the photoelectric effect. So it was observed that metals can emit electrons when a light shines on their surface, and that's called the photoelectric effect. Classic wave theory says, well, the light energy is being transferred to the electron, and when it gets enough energy, the electron will get kicked out of the atom. This would predict that only the amplitude or the intensity of the light would affect whether electrons are emitted or not. So if you had a bright light, you'd get electrons being emitted. If you had a dim light, you maybe wouldn't get any electrons. Or there might be a lag time. So the electrons are absorbing the energy from the light, and so it might take a while before the electron gets enough light from this dim light to be ejected. Here's the setup. You have an evacuated chamber, because if you have any gas in there, it catches the electrons. So we have a metal surface here. We're going to set this up, attach it to a voltage source. So we have this metal surface that the light is shining on, and then we have another electrode over here. This is the positive terminal, that's the negative terminal. So normally there would be no electric current flowing through empty space. But when light hits this metal and ejects electrons, the electrons are going to be attracted to this positive terminal, and so they're going to come over here. And our meter is going to detect that. So we can see by looking at this meter when electrons are being ejected. So this is a graph of observations here. So the rate of electron ejection would correlate to how much current you see versus the frequency of the light. So at low frequencies, nothing happened. No electrons were ejected. And it doesn't matter how long you wait, they won't be ejected. When you get to the threshold frequency, all of a sudden you get a lot of electrons being ejected. So it jumps up, and there's a little bit of a curve here, but then beyond that, going to higher frequencies does not change how many electrons are ejected. We do see an effect of intensity. Lower intensity light gives us a lower rate of ejection, and higher gives us a higher rate, but we do not see the predicted lag time between them. At a high enough frequency, even a very dim light will eject electrons. So this does not match up with the predicted things. Lost my words. So how do we explain this? Well, Einstein to the rescue. He proposed that light energy was delivered to the atoms in packets. Essentially, he's saying, well, light is a particle. So that light particle or packet is called a quantum or a photon. A photon is a particle of light. The energy of that photon is directly proportional to its frequency. High frequency, high energy. And that's the same thing we saw with waves of light, right? The energy is inversely proportional to the wavelength. So the proportionality constant here is given the symbol h, and that's Planck's constant. It's 6.626 times 10 to the minus 34 joules times seconds. We may need to use that in calculations. I'll give that to you on an exam. You don't have to memorize that one. So we can say that energy is equal to h nu, Planck's constant times the frequency. We know that frequency is the speed of light divided by the wavelength. So we can also say that energy of this photon of light equals Planck's constant times the speed of light divided by the wavelength. So we could do some calculations. A 100-watt light bulb radiates energy at a rate of 100 joules per second. The watt is a unit of power. Power is energy over time. So a watt is equal to joule per second. So a 100-watt light bulb, 100 joules per second. So if all of the light emitted by this light bulb has a wavelength of 525 nanometers, how many photons are emitted per second? And they're saying assume 3 sig figs. Because the way this is written, it would only be 1. But we're going to use 3 sig figs. Well, let's write down what we've got here. We've got 100 joules divided by seconds, and we've got 525 nanometers. And we want to know number of photons. This is a problem that requires some critical thinking. It's not an obvious, oh, plug it into the equation and get this answer. So this is giving us energy per second. We just learned about this equation, E equals hc over lambda, that gives us the energy of 1 photon. They told us what the wavelength was. Could we calculate the energy of 1 photon? Sure. It's hc over lambda. H is 6.626 times 10 to the minus 34 joule seconds. Just going to go back and check that because 6.626 times 10 to the minus 34 joule seconds. So that's just this guy right here. C is the speed of light. 3.00 times 10 to the 8th meters per second. And we're going to divide by the wavelength, 525 nanometers. Look at the units. Seconds cancel. Do meters cancel with nanometers? No. So we can employ the same little shortcut that we did earlier. Instead of writing nano, the symbol N, I'm going to write what it means. So 525 nanometers is 525 times 10 to the minus 9 meters, because nano means 10 to the minus 9. And then meters cancel meters. So I got 6.626 EE minus 34 times 3 EE8 divided by 525 EE minus 9. They told us to use 3 sig figs. 3.7862 times 10 to the minus 19. And what's the unit? Joules. That is a really small number. That is the energy of one photon. What are they asking us to find? The photons emitted per second. So that's how many photons in 1 second, right? So this many joules is equal to 1 photon. So there's 2 different ways you can think about this. You can say, well, here I have 100 joules per second. So I could convert joules to photons, and then I'd have photons per second. Another way to do it is to say, well, I have 1 second, how many photons? So if I have 1 second, I can convert that to joules, because I know there's 100 joules per second. And I know the energy of 1 photon, so I can convert that to the number of photons. And that's the number of photons in 1 second. So that might be the one that's more straightforward. So 1 second, and I want to convert to joules. I'm going to divide by seconds. And then I want to convert to photons. I need to divide by joules. Dimensional analysis. For this problem, what's the relationship between joules and seconds? 100. They told us that. 100 joules per second. So 100 joules per second. And the relationship between photons and joules is this guy down here that we calculated. 3.7862 times 10 to the minus 19. So then we do the calculation. 1 times 100 divided by 3.7862 times 10 to the minus 19. 2.6411 times 10 to the 20th. So we were instructed to use 3 sig figs, so 2.64 times 10 to the 20th photons in 1 second. That's a lot of photons. Any questions? So, by understanding how to cancel out units, we can put these sorts of problems together just by looking at how can I get the units to cancel. So here's a practice problem. Arrange these 3 colors of visible light, green, red, and blue, in order of increasing wavelength, increasing frequency, and increasing energy per photon. So this is the sort of problem that you should be able to do on an exam. and I'm not going to give you the electromagnetic spectrum on the exam. So I'm going to talk you through this. This is how I would answer the problem. It actually involves a lot of talking to myself in my head. So I'll say it out loud for you. So we got 3 colors: green, red, and blue. What order do those occur on the spectrum? Red, green, and blue, yeah. Roy G. Biv, right? So I'm thinking Roy G. Biv. So there's blue, there's green, and there's red. So these 3 different orderings, green is always going to be in the middle. It's either going to be red, then green, then blue, or it's going to be blue, then green, then red. There's no way around that. Next, I need to figure out, well, which end of the spectrum is red on? Which end is blue on? How can I figure that out? The way I remember this is here's violet. Ultraviolet is next to that, right? So we've got the visible light, and then we've got the UV. Which is going to give you a sunburn? Visible light or ultraviolet light? Ultraviolet light. Why? Because it has more energy. So this is the high energy side, and the other end is the low energy side. Just kind of reasoning it out. Roy G. Biv, I get sunburns, I can figure it out. I do not keep this in my head. There's just too many other things I need more often, and so this I just have to think about it every single time. So we can answer one of these now, right? Energy per photon. The energy of the light is the energy of the per photon. So this is asking us to arrange in order of increasing. A lot of students get these exactly backwards, and so I want to be very clear. Increasing. So that means the first one is the lowest, and then the next one's bigger and bigger and bigger. And so as you go through the list, everyone is increasing. That's what order of increasing means. So I want to put the low energy one first. So that's the red at this end. So you could put these in just as a list separated by commas. I prefer to put in the greater than, less than signs just to be doubly clear on what I'm doing. So the red is less energy than the green, which is less energy than the blue. Those greater than, less than signs can be a little confusing too. But there's a small end and a big end, right? The big end, this open end, points to the thing that's larger, and the tiny pointed end goes to the thing that's smaller. So there's my arrangement for energy per photon. Any questions? Now we've got wavelength and frequency. And so I might draw a picture here. So I'll think about wavelength. So I'll draw a wave with a long wavelength, and I'll draw a wave with a short wavelength. Which of those looks more energetic? The bottom one, right? This looks like a crazy thing just jumping up and down, right? And this looks slow, right? Now, they travel at the same speed. But if you're standing over here, this one's going to hit you just every once in a while, and this is going to hit you bang, 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 right? This is high energy. This is low energy. So this one's higher energy, and this one up here is lower energy.
So the bottom one would be blue, the top one would be red.
Yes. The bottom one is blue, because blue is at the high energy end. The top one, being low energy, is going to be the red. So we can look at this and see, well, this is a long wavelength. And so if I want to go in order of increasing wavelength, I want the longest wavelength at the end. So the longest wavelength would be last. That's the red. Longest. And which one has the shortest wavelength?
Blue.
The blue. So blue is the short wavelength, green is in the middle, and red is at the high end. how long the wave is. Frequency and wavelength are inversely related. So you can remember that and say, well, it's got to be opposite. Or again, you can look at these. This is the red one. This is the blue one. And say, well, which one is going to hit me more frequently if they pass at the same speed? Well, this one's going to hit more frequently, right? Higher frequency. Okay, so that's the largest. I want to put that at the end of my list. And red must be the low frequency, and so that goes at the other end, and I put green in the middle. So I can answer a whole bunch of questions like this by understanding a couple of basic things. I draw my picture and identifying, I think we can all just look at the picture and say, well, this is long wavelength and this is short wavelength. Think about these things passing you. How frequently do they hit? You can look at that. You do have to have this Roy G. Biv idea, and that ultraviolet is higher in energy than violet. And that gives you the original direction. Any questions? So back to that photoelectric effect. Understanding light as a particle explains the photoelectric effect. So at that threshold frequency, one photon has just enough energy to kick an electron out. Psi is the binding energy of the electron. It's a circle with a line through it. That's a Greek letter. If we irradiate the metal with higher energy photons, they also have enough energy to kick out the electrons. But the electron also gets more energy because it's got to absorb all the energy of the photon. So it has enough to get out, and what happens to the extra energy? It's kinetic energy of the electron. So the kinetic energy of the electron is the energy of the photon minus the binding energy. The energy of the photon is h nu, because we learned that the energy of a photon is equal to Planck's constant times the frequency. And we're subtracting the binding energy. Okay, so this is a little bit like going to Disneyland. So think about the electron is a little boy going to Disneyland, and you get up to the gate, and you're like, I want to go in and ride the rides. And what's the attendant going to say? Where's your ticket? You've got to pay to get into Disneyland, right? The gate fee, the ticket price to get in, is the binding energy. If you don't have enough energy, if you don't have enough money, you don't get in. So here, the electrons are getting out. So that's a little backwards, but the electrons are getting out, the boy's getting in. If you don't have enough, you don't get in. Not even for a little bit. It's either you get in or you don't, right? What if you have more than enough money? Will they let you in? Yeah. Will they take all your money at the gate? No. They're just going to take the ticket price. You take the rest of the money in with you. Now, what's the little boy going to do with that extra money at Disneyland?
Spend it.
He's going to spend it. He's going to buy candy and souvenirs and stuff, right? That's the kinetic energy of the electron. So the photon comes in, and the binding energy is spent just to get the electron out of the metal. The ticket price just to get the kid into Disneyland. The difference between the energy of the photon and that binding energy is the stuff that's left over. So the kid comes in with a wad of money. It's too much. It's more than enough to buy a ticket. He buys a ticket. He keeps the rest of it. He goes in and he spends it on other things. Does that make sense? So the higher the energy of the photon is not going to cause more electrons to be removed, but it's going to cause the electrons that are removed to move faster. They're going to have higher kinetic energy. So suppose a metal will eject electrons from its surface when struck by yellow light. What will happen if the surface is struck with ultraviolet light? Well, we first have to figure out which has more energy. So Roy, G, Biv, which end of this is high energy? The violet, because ultraviolet gives me a sunburn. So this is high energy. So which is higher in energy, yellow light or ultraviolet? Ultraviolet. So the ultraviolet is higher energy than the yellow light. So we kind of need to establish that before we look at the choices. So yellow light was enough to eject electrons. If I shine ultraviolet light, will I get no electrons ejected? No. That would happen if I shined red light on it, because the red light is lower in energy. And we're told that the yellow is just enough. So it's not choice A. Electrons would be ejected, and they would have the same kinetic energy as those ejected by yellow light. Nope. Because they both pay the same amount of binding energy. The ultraviolet photons have more energy. This is a kid coming in to go to Disneyland with more money. He has more money once he gets in. They don't go in with the same amount of kinetic energy. So that one's not true. Electrons would be ejected, but they'd have greater kinetic energy than those ejected by the yellow light. Yeah, that's the true one. So the higher energy photon is going to pay the binding energy, and then the leftover goes into kinetic energy for the electrons. So this is the correct choice, and then this one is also wrong. Electrons would be ejected, but they'd have lower kinetic energy. That one's not true. Any questions? So here we get to the Schrodinger's cat kind of idea. Wave-particle duality of light. So light can behave as a wave. We observed that with the double slit experiment. Light can also act as a particle. We observed that with the photoelectric effect. Which behavior you see depends on the experiment. But by observing it behaving, it's going to act like one or the other. It won't act like both at the same time when we're watching. And more on that later.